Here we have another interesting problem. Here, a uniform rod of length L lies on a smooth horizontal table. That means there is no friction between the rod and the table. A particle moving on the table strikes the rod perpendicularly at one end and stops. That means if we want to draw this is a rod which is lying on the table, and this is its center, say. A particle here, a small particle here, is moving in this direction, and it hits the end of the rod or tip of the rod and stops there. Length of the rod is given L. So we can easily see that whatever the momentum of this particle, if it's a very little momentum, momentum will impact to the tip of this rod, and the rod will have some motion. As earlier, what will be the rod's motion? Rod's motion will be both linear as well as both translational as well as rotational. The new position of the rod may be something like this. Maybe after some time, the rod may take this kind of a position. So this is the center of mass of the rod. The center of mass of the rod moves from, say, point P to point Q. And tip of the rod moves, say, point R to point S. This will be the situation. Now, what are the questions? Question is, find the distance traveled by the center of the rod. That means to what distance this center of the rod travels. What is the PQ distance? By the time it turns through a right angle, by the time it turns through pi by 2. Okay? So let us attempt the first part. First part is part A. We consider, let's take this little darker green, part A. Let us assume, because mass of the particle, etc., nothing is given, so we have to make some assumptions. Assume mass of the particle is equal to m, and velocity of the particle is v1. Also, let us assume mass of the rod is capital M, mass of the rod is equal to capital M. Also assume velocity of the center of mass of the rod after collision. After collision is equal to, let us say it is V2. Then we can, after these assumptions, we can start. So what was the momentum of the particle? Momentum of the particle was momentum of the particle was small m and to v1. And momentum of the rod after collision, momentum of the rod after collision is equal to capital M V2. Now you have already guessed what I am, where we are heading to. So by conservation of momentum, by the law of conservation of momentum, this mv1 equal to capital mv2 or capital M v2 equal to small m v1. From here we get the velocity, linear velocity of the center of mass v2 is equal to small m by capital M and v1. This is, let us call it relation 1. We shall need this relation later. Now going to the second step. I change the color for your benefit. We go to the second step. Now we consider the rotational effect on this. Momentum imparted, momentum of the particle, this particle applied a moment, the particle applied a momentum small m v1 at the tip of the rod of the rod. Now what is angular momentum? Angular momentum is the momentum of the force which has been applied multiplied by the distance, perpendicular distance between the direction of the force applied and the center of rotation. So angular momentum, angular momentum of the rod is nothing but the distance L by 2 multiplied by mv1. This angular momentum is also equal to I omega. That's right. Angular momentum is equal to moment of inertia I multiplied by omega. So what do we get? So I omega is equal to mv1l by 2. Now what is I? Moment of inertia of the rod around its center is ml square by 12. ml square by 12 into omega is equal to, on the right hand side we had mv1 capital L by 2. From here you get the value of omega very easily. So omega is equal to 6mv1 by capital M into L. But they did not ask for the value of omega. They asked for something else. What they asked? How much the center of mass travels by the time the body turns by right angle. So with this value of omega, we have to find out how much time is required for a rotation by right angle, pi by 2 radian. So we write time required required to rotate by an angle of pi by 2 is equal to pi by 2 divided by omega. So this is ml, this is pi, let's not forget, ml by 6 small m v1, right? Now, this is the time required. The velocity of the center of mass, we have already found this v2 is equal to small m v1 by capital M. So we have to find out simply how much the center of mass moved within this time. So that's not difficult at all. So the center of mass moves by, the time is given pi capital M L divided by 12 small m v1, and velocity of v and the velocity v2. Let me write velocity v2 here because it will be easier for you to remember it later on. So just one more step it makes, m pi ml by 12 small m v1, that multiplied by v2 is small m v1 by capital M. Now a lot of things are now cancelled. Capital M gets cancelled. Small m gets cancelled, and v1 gets cancelled. So what we are left with is pi L by 12. So pi L by 12. So this is the first answer. That means by what distance the center of mass moves by the time the rod rotates by 90 degrees or pi by 2. Then we go to part B, second part of the question. Second part of the question is, see it very carefully, show that if the mass of the rod is 4 times than that of the particle, the collision is elastic. Right? You remember what is the condition of elastic collision? Condition of elastic collision is the elastic collision is the relative velocity before the collision will be equal to the relative velocity after the collision. Here, the rod was still or static before the collision, and the particle was moving. So it turns out to be if the tip of the rod where the particle struck the rod, if the tip of the rod velocity comes out to be velocity of the particle, then the collision was elastic. Not, mind it, not the velocity of the center of mass, because the small particle, it hit the rod at its tip. So we have to find out the total linear velocity of the tip, right? Now, for your benefit, I do the drawing once again. Say this is the rod. Say this is the rod before collision, and this is the particle which hit it. After collision, the center of mass moves here, and the rod takes a turn like this. And this is the tip of the rod. This is the tip of the rod. Now, this tip of the rod, how do we find the linear velocity of the tip of the rod? It will not be difficult. Just wait and see. We can easily find out the linear velocity of the tip of the rod. Now, when the rod was first hit immediately after collision, it started turning, and let us say at that time the tip of the rod has a tangential velocity v0, with which and this tangential velocity gets transferred here. The tip of the rod has a tangential velocity, right? This tangential velocity v0 is of course equal to omega multiplied by this distance, which is L by 2. So say the tangential velocity of the tip of the rod after collision equal to V0, right? Then, of course, we can say V0 equal to omega multiplied by L by 2. This is clear. This is L by 2. This length is L by 2. V0 equal to omega L by 2. Omega we already know, which we have already found 6 mv1 by ml. So 6 mv1 by capital M L, that multiplied by capital L by 2. So this is equal to 3 mv1 by capital M. 3 small m v1 by capital M. So we have got the tangential velocity of the tip immediately after rotation. And the fact is, the center of mass also has a velocity. This is the velocity of the center of mass, which we have considered V2. Velocity of the center of mass we have considered V2. Velocity of the center of mass we have already considered V2. Now, then what is the total linear velocity of the tip? Let me write here. Also, velocity of the center of mass is equal to V2, which is equal to mv1 by capital M. So, the tip has a total velocity of summation of these two velocities. So, total linear velocity of the tip of the rod is equal to mv1 by capital M, one velocity, plus there is another velocity we have got here, 3 mv1 by capital M. This makes equal to 4 mv1 by capital M. Now we have almost reached the point. Now, if the collision is elastic, if the collision was elastic, then velocity of the particle will be equal to net velocity of the tip of the rod. And what was the velocity of the particle? We considered, remember here, we considered velocity of the particle to be v1. That means this was considered to be v1, right? Velocity of the particle was v1. That means, that means, that means 4v1, sorry, 4mv1, that means 4, that means 4 mv1, mv1 by capital M is equal to v1. So v1 gets cancelled. So we get the condition capital M is equal to 4m. That is, mass of the rod, mass of the rod is equal to 4 into mass of the particle. So this is proved. Fine. So we ended this problem here. Now we go to the next problem.